So this video is meant to be either an introduction to or a review of factorials. You may have some familiarity with them from some previous course that you've taken, but if not, they're great because a factorial, right, is denoted by this exclamation point after some number, so it makes everything seem really exciting. And if you look over on the right, we have a formal definition of a factorial, which is, right, if n is 0 or 1, right, n factorial is 1. I know that seems a little weird. It makes sense that 1 factorial would be 1, but 0 factorial is also 1, and we'll talk about why in a second. And then otherwise, right, if n is greater than 1, it is just the product of n and then every integer less than n, but just down through 1, okay? And now it kind of makes sense why 0 factorial has to be 1, right? Otherwise, if it were 0, everything would just come out to be 0 at the end, all right? So, for example, if you look at number 1, 4 factorial really means 4 times 3 times 2 times 1, which comes out to be 24, right? 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which, if you notice right here, is 4 factorial. So we can say that 6 factorial is 30 times 4 factorial, which is 30 times 24, which I believe is 720. All right. And then 10 factorial, right? Again, let's use a shortcut, right? 10 factorial is going to be 10 times 9 times 8 times 7, and then times 6 times 5 times 4 times 3 times 2 times 1. So we'll just say times 6 factorial, and we know what that is, okay? And if you do all that math, and you can check this in your calculator, I believe you get, what is it, 3,628,800. Yeah, these get out of control pretty quickly. All right. So now, doing these by hand can take a while, and there is a way to do them in your calculator. All right, so to compute, say, 20 factorial, you would punch 20 into your calculator, right? Then you would hit the math button, select the prob option, and then the fourth menu item down is the factorial symbol, and you hit enter. And I kind of wish I hadn't given 20 as an example. This might be too big for your calculator to handle because it is a giant number, but you can try it with, with a 6 factorial and just confirm that you actually get the 720 that we got up here. All right. And so now if you've been familiar with factorials in the past, you've probably been doing what we did in examples 1, 2, and 3. All right. But for the scope of this course, we're going to be interested in manipulating factorials symbolically, right? So for number 5 here, n factorial, we're going to sort of see this over and over, and we want to know that it means, right, whatever number n is times the number just beneath that, so n minus 1, the number just beneath that, so n minus 1 minus 1 again, so that's going to be n minus 2, right, times n minus 3, and so on and so forth, and you're going to multiply, right, all of those out until you get all the way down to 1. Okay, so we're going to get sort of comfortable expanding this into this. All right, and if you look at number 6, right, a little bit more complicated, but exactly the same idea, right? 2n plus 1 factorial means take the number 2n plus 1 and then multiply it by, right, the number 1 less than that, so that would be 2n plus 1 minus 1, so just 2n, and then the number 1 less than that, so 2n minus 1, and so on and so forth, again, until we're all the way down to times 3 times 2 times 1. Okay, pretty easy, right? All right, next page. Okay, and now, all right, I want to get to this idea of simplifying an expression that uses a factorial. All right, this is going to be integral, in being able to work with some different sequences and series. All right, so if you take a look at number 1, right, we have 5 factorial over 7 factorial, right? And really that's 5, where's your little hat? There we go, times 4, times 3, times 2, times 1, over 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1, and we notice what's going to happen here, right? These 5s are going to cancel, the 4s are going to cancel, the 3s and the 2s and the 1s are going to cancel. So we really didn't need to expand the factorial at all. We could have just written 5 factorial over 7 times 6 times 5 times 4 times 3. Oh, well, that's just 5 factorial again, right? And then these do indeed cancel, and you're left with 1 over 42. Now, moving on to example 2, we're going to try to go with that same idea, but we want to be careful because factorials don't necessarily work the way we want them to. We cannot say that 8 factorial times 3 factorial is 24 factorial, or that 8 factorial times 3 factorial is 11 factorial, right? You really have to handle them each independently. All right, and again, a helpful trick, and you'll see this below, is that we really want to focus on expanding the number that's bigger, right? So, right, 11 times 10 times 9 times, oh look, 8 factorial, right? And then these can cancel, and that leaves us with 3 factorial, right? Which is 3 times 2 times 1, that's 6. Over, let's see, when you work that out, you get 990. And then that reduces to 1 over 165, I think. Okay? And then example 3 should be easy, all right? I sort of compare my numerator and my denominator. The 59 factorial is bigger, so that's the one that I want to expand because I expect that it will encompass the term in the denominator. So we'll do 59 times 58 times, yes, 57 la-di-da-di-da, so 57 factorial. And then that's exactly what's downstairs. So these cancel, and then you're left with 59 times 58, which is 3,422. And we can translate this idea to working with symbols, okay? So in number 4, right, we want to think which one is bigger, right? N minus 2 or n? Well, obviously n is going to be bigger because we're only working with the positive integers here, well, n0. All right, so n has to be bigger than n minus 2. So n is the term that we will expand to simplify. All right, so n minus 2 factorial over, well, n factorial is going to be n times n minus 1 times n minus 2, and then everything below that, so n minus 2 factorial. And then these cancel, and this becomes 1 over n times the quantity n minus 1. And isn't that so much easier to look at and work with? All right, let's try again for example 5. All right, so again, considering that n has to be non-negative, I would say that 2n plus 2 is bigger than 2n, so that is the term that we will expand and hope that some things will cancel. So we'll have 2n plus 2 times 1 less than that, and 1 less than that, and there it is, 2n factorial. So that is what's in the bottom. These cancel, and we are left with, right, 2n plus 2 times 2n plus 1. Easy. Now, the one in number 6 is a little bit trickier. You just have to be careful because, again, we don't quite know, right? N factorial squared, like what do we do with the squared? How do we handle that? Can we like distribute it in somehow, right? We don't really know. It's sort of hard to apply those types of properties to factorials. But if you just rewrite it, we do know it at least means this, right? So if we rewrite it like this, now we're like, all right, this is something that I can work with. And notice, all right, when we consider this term in the denominator, it is larger than at least one of these, right? Or I'm sorry, the n factorial is larger than the n minus 1 factorial. However, the n plus 1 is larger than the n factorial, right? So what we're going to want to do is expand this so that it cancels some stuff from here, but then expand this so that it cancels some stuff from here. All right, so that's exactly what we'll do. And n factorial is, again, n times n minus 1 times, oh, well, we can stop there because we have the n minus 1 factorial in the denominator. All right, and then we have this other n factorial here, and we will expand the n plus 1 factorial. So n plus 1 times 1 less than that, and oh, there it is. Right, there's our n factorial. So these guys cancel, and we are just left with n over n plus 1. Much prettier, don't we agree? Okay, next page. So now here we look at a sequence that is defined by a set of factorials, right? And we could very easily plug in, right, you know, for a sub 1, 1 factorial over 1 plus 2 factorial, and start generating some terms of the sequence, right? So we'd have 1 factorial over 1 plus 2 factorial, which is 3 factorial, which would be 1 over 6, right, for your a sub 1. And then a sub 2 would be, let's see, that would be 2 factorial over 2 plus 2 factorial, so that would be 4 factorial. 2 factorial is 2. 4 factorial is 24, right? So in this case, right, a1 would be 1/6, and a2 would be 1/12, right? And then our goal is to see if the sequence converges, all right? And we found analytic techniques to do this in section 9.1, right? We said the sequence will converge if the nth term converges to a certain number, okay? But, well, here's the expression for the nth term, and we don't really know how to work with this analytically necessarily to see if it's going to converge to something. But fortunately, because we now know how to simplify expressions with factorials, on the previous page, we simplified this very same sequence and found out that it's equivalent to 1 over n plus 2 times n plus 1. And it is very easy to see if that nth term is approaching a certain number, right? We simply take its limit, letting n get arbitrarily large, right? And then this is an easy limit to do because the denominator is just going to get huge, right? So this fraction is just going to tend toward 0. So this does indeed converge, and it converges to 0. All right. Now for this example 2 here, we have also simplified that factorial expression, right, that sequence. You could go ahead and generate a couple terms of the sequence if you like, but at this point we can kind of just cut to the chase, right? We know that this expression simplifies to n over n plus 1, right? And so when we think about long-term behavior, right, as n gets large, are the individual terms of the sequence trending toward any one particular number? Well, when we initially substitute, right, we get infinity over infinity, but we know that's not a big deal because we just use L'Hopital's rule. And so we take the derivative of the numerator and the derivative of the denominator, and we get 1. And hopefully, if you were generating terms of the sequence, you would see that they were trending toward 1. All right, and last but not least, sequence C, in number 3, we had simplified that expression, and it came out to be equivalent to the quantity 2n plus 2 times 2n plus 1. Right, and then again, right, if we generate a few terms of the sequence, right, by just plugging in for n and evaluating the factorial expression, hopefully we, see what our analysis tells us. Hopefully they're in agreement, right? But what's going to happen here, right, as we let n go to infinity, well, stuff's just going to get big, right? It's sort of like an infinity times infinity situation. So I would say that this goes to infinity, and so because the terms are just getting arbitrarily large, over time, I would say that this one diverges. Okay, and that's sufficient. All right, so hopefully you now have all of the groundwork necessary to keep moving forward with our sequences and series.